Hey, what's up, everybody? So we're going to concern ourselves with motion in essentially symmetric field. And what this looks like is, well, first to show some motivation for this, let's say we have some position vector that is the difference between two other position vectors, okay? We can reduce this to some, and of course we would have some potential as a function of this new vector that we created. And we can, represent the Hamiltonian. Just want to show you that linear algebra kind of exists. So if we have the Laplacians here, we can basically have the liberty to split them apart, or just kind of sum them together and have this potential as a function of the difference between them. And so this is just something that mathematically works out. And so what we want to do now is define some new coordinate. Let's call it r. And it's going to be m1. You'll probably have seen this before. m2, r2 divided by m1 plus m2. All right, so here's our coordinate, and then let's have some, let's invent some relative coordinates between them, which we had as the magnitude, or we can just have it as the difference between the two vectors. The Hamiltonian will look something, or it'll take on a form like this, where if we have, and actually, it's going to look like this, where we then can take the Laplacian of this coordinate here, and also of this reduced coordinate here. Just, assuming that that's correct. And so the Hamiltonian is going to look something like this. And this m here, this little m, without any indexes or whatever, is going to be the product of m1 and m2, divided by m1 plus m2. Okay, this is what we usually call in classical mechanics the reduced mass, and it's usually as mu, but we can just use m. Okay, so the wave function then is let's talk about the wave function. Okay, it's going to be a product of this big R and this little r. Okay, we have this this center of mass coordinate, if you didn't realize that it was a center of mass, and the reduced mass. Sorry, not the reduced mass. I think it's like relative. I think they call it like relative coordinates or something like that. We just have two, position vectors, and it's the difference between them. So center of mass, relative coordinates. We're gonna have a function, or we're gonna make psi a function of both of these things. And it seems like an ugly kind of thing to do, but the reason why we would want to do such a thing, well, first of all, we can do this in any differential equation, which is separate the variables, or look at the class of solutions where the variables are separated from each other like this. The motion of the center of the mass is that of a free particle in this case, and the relative mass is described by or the relative motion here. That's what we want to call it. This is like a relative motion, pretty much. It's described by the Schrodinger equation for a single particle of mass m in a potential. Okay, so we can think about this as just some particle in a central field, so 2m. Okay, where we're adopting this notation here, and we can do the Laplacian acting on the wave function here. The potential in the wave function is equal to basically it's a stationary state. And, the reason why we can do this is because angular momentum, as we discussed previously, is conserved in a central field. Okay, and so we can seek kind of these stationary states that are also eigenfunctions of L squared and L hat. So really what this is going to look like, let's clear the page. What this is going to look like, of course, we're seeking eigenfunctions now. These guys here. So what this is going to look like is if we separate the variables in spherical coordinates, of course the solution needs to look something like this. We would have some capital, R function that is a function of the relative coordinates. you know, with this form, which you remember previously. These are the spherical harmonics. Okay, these are a set of our of these shared eigenfunctions for these quantities here that we are allowed to measure from the angular momentum. Okay, and so when we separate the coordinates here, we get this. Okay, and if we substitute into the Schrodinger equation using the spherical coordinate form of the Laplacian, and the fact that these are the eigenfunctions of the angular part of the Laplacian, and which is just the negative. This is the negative of so this is basically the angular part of the Laplacian. Eigenfunctions of the angular part of the Laplacian. I guess it would be the negative of that. You know what? I'm not being clear. Sorry. Let me just you'll see what I mean. I'm just stepping ahead. But we'll obtain something called the radial Schrodinger equation, okay? So this is called the radial Schrodinger, that's what the Germans say, but Schrodinger equation, okay? The radial Schrodinger equations for the function for r's r, okay? It's going to look something like this. So we have r squared, whenever r squared dr r squared d capital R. So d capital R is like the function, okay? The radial part of the function. And we'll have L times L plus 1, which are the eigenvalues for the orbital angular momentum acting on this R, capital R, times 2. And remember, we're in the reduced mass kind of representation of our system. Okay, and have r is equal to 0. Okay, so we have this radial Schrodinger equation. Okay, and to make this, we can do this really convenient. We can do this convenient substitution or change a variable here, which we can just say r times little r times big R of r is equal to chi of r. I used to have this professor that would say, you know, chi a as in yippee or whatever. I don't know. Just thought that was funny. He would always say that when we're doing like mixing problems and stuff in PChem. But yeah. So, anyways, that was kind of a tangent. But if we just do d2 by chi as in yippee, we have over to h squared. You know, just simplifying out things. Honestly, your ability to do differential equations is entirely contingent on your ability to make intelligent substitutions like this, because this is way better to think about. Okay? Like, you can literally transform entire differential equations, like, you know, some massive, you know, Black-Scholes equation into a Schrodinger type equation or something. It's the subject of my research that I've been working on, but yeah, so I mean, that's that, right? So this is we got it into a better form where it's a function of chi instead. And so just philosophically, right, what is this? This equation here just is formally identical to the one-dimensional Schrodinger equation for a particle moving in an effective potential. Okay, so really, this is like a kind of some effective potential, basically. So we have a one-dimensional Schrodinger equation from the radial equation, and you know, the second term here is kind of like this term here. It's got kind of a name. I think it's called by Landau the centrifugal energy. It's kind of like this repulsive potential that pushes the particles with this like non-zero angular momentum away from the origin. And this problem of like 3D motion kind of in a central field is now reduced to a one-dimensional problem on the half line r is greater than, for little r is greater than 0. So just assuming that little r is positive, we can have this one-dimensional representation of that three-dimensional system. And so, yeah, that is very convenient. So really what we can do now is say that the wave function must be finite at the origin, which means that, you know, this thing also has to be finite, or just less than infinity. It can't blow up anywhere. And since we have that this chi function is equal to r times big R, this implies some boundary condition then that chi of 0 should also equal 0. Okay? And hopefully you can see why, because near the origin, you know, assuming that this is less singular than 1 over r squared, the centrifugal term that we were kind of talking about, or centrifugal term, dominates the equation, because the second derivative of chi with these orbital angular momentums here divided by r squared, basically, and it's, of course, it's scaling chi itself, basically just goes to 0. So, you know, that term will basically kind of dominate, and so the solutions would be r plus l plus 1, and the proportionality of chi with r to the negative l. Okay? And so then the boundary condition, really, this boundary condition here selects the first solution. So we kind of get it kind of for free. So for small r, we get this proportionality. So hopefully that's neat. We can kind of see this relation that happens from and hopefully you didn't. Hopefully you can see that this is the equation that we're interested in, right? Which is 2m over h bar times e minus u of r minus just so you can reference it, 2m r squared times, I guess, l times l plus 1 times chi is equal to 0. Okay, so hopefully you can see this, right, that, you know, it's got to be finite, and we can impose this constriction here, and that, you know, this guy is less singular than 1 over r squared, and hence we can then get these kind of approximations here, okay, from those assumptions. Hopefully that makes sense. If not, you know, I would recommend looking at Landau and Lifshitz book. It's probably the best quantum mechanical book out there. So, okay, so for a free particle then, let's say we have u of r equals 0. The radial equation for chi of r then is going to look something like this, where we have the chi double prime. Let's just, I don't know what I'm doing here. Okay, so u of r is equal to 0. Okay, we want to see this for a free particle. So let's do let's parameterize this a little more intelligently, so that we don't have to write too much stuff down. Okay, it's equal to 0, and of course we just have to define k once, which is this term that keeps coming up, which is the square root of 2me divided by h bar. Okay. All right. So the solution satisfying the condition, of course, that the initial condition should be 0, are related to these things called the spherical Bessel functions. Okay, these spherical Bessel functions, and they look something like this, where if I had r of k and r of k and l for some little as a function of little r, I should get some kind of, these are like normalization constants here, for some k, and then we have j here with little l, as a function of k times little r. Okay, and the asymptotic form for large distances. So just basically, if we had for a very large L, we should get a standing wave. So standing wave. This is a nice property of the Bessel functions, which basically just tells us that in this limit here, this should look something literally like 1 over r sine of kr minus l pi over 2 times a little phase factor here, but it's literally just a standing wave asymptotically. Okay, and so for a particle, moving in potential u of r that falls off, really suddenly fast, the asymptotic solution is similar to this, but with a phase shift. So you can think about just for I guess let's see, if the potential just kind of falls off really fast, like something like that, basically, it'll have something, but with like this phase shift that depends on the angular orbital angular momentum. And so we just say, something like this, very similar. Sorry, I'm constructing it from the inside out of the sine term, because that's like important. That's like the sine, and then of course just some constant or whatever times that. It'll look something like this. Okay. Yeah. So very interesting things. That's kind of like a spherical wave, if you will. Solution for a spherical wave. Just in terms of spherical Bessel functions. All right. Now let's look at the resolution of a plane wave. Let's try to resolve a plane wave. So if we had a plane wave, e to the I k dotted with r, and this is just a particle with definite momentum. Okay, we know. Remember, plane waves are the eigenbases or the eigenfunctions for momentum always. So p is equal to h bar, say some k vector. This can be expanded to this series of spherical waves. So you can actually show a plane wave as a series of spherical waves, which represent the states of definite angular momentum. Okay, it might be a little confusing at first, but if you choose the z-axis, okay, if you choose the z-axis along k, okay, such that I guess k dot r is equal to kr cosine theta. Okay, we can then have that the e to the ik z, because we want to look at the z back. We want to do a reading of the z-axis for that plane wave. It would look something like the sum over all the orbital angular momentums times some imaginary number exponentiated to that for some reason. Haven't really dug into the math of why that is, but looks something like this form. The Legendre polynomials. So it's going to look something like this. But basically, the whole point is that you can resolve a plane wave in terms of the angular momentums. All right, and it's pretty good, and it's rewritten. Basically, you rewrite it as a sum of outgoing. So it's like a sum of outgoing and ingoing spherical waves. Okay, so for outgoing and ingoing spherical waves, I guess whenever the parity changes on the orbital momentum, that's probably what it means by outgoing and ingoing. That's my guess. Okay. Yeah, that's interesting. So you can basically represent this plane wave in the z axis in terms of this. Very cool. All right. That's fun. Let's look at a particle falling into the center. Okay. And what I mean by this is, let's consider a potential where the origin behaves basically like this, where we get some constant beta times r squared. Okay, so just a potential that is a lot stronger, I guess, towards the origin. Okay, and the radial equation then for some small r, we would use the same approximation that we did earlier, and this isn't an x, this is a chi. Which looks something like this here. Minus L plus 1 divided by r squared. Chi is equal to 0. Okay, this could also kind of, let's just say this implies just some basic form here. I want to simplify it out. Let's call this gamma. Let's call this gamma. It's big old constant. Basically, I hope you see like this constant we're calling gamma over r squared chi is equal to 0. All right. So gamma, of course. Let's just write it out. Equals m2 beta divided by h bar squared minus L plus 1. Okay. And the solution then, the solution is chi is proportional to rs, r to the s, where s times s minus 1 plus gamma is equal to 0, giving this condition here, where we have s is equal to 1/2 of 1/4 minus gamma. Okay, so let's look at the cases of this. So let's say case 1. Case 1 gives us that if we have gamma is less than 1/4, the roots then for s would be real, and so the boundary condition. So basically, when it's real, the boundary condition we composed, or that we just supposed to be correct. Sorry. It can be satisfied. Okay. And normal stationary states exist. Okay. So for real roots, we get the satisfaction of these things. But let's look at case 2. That's not the case. So if this happens, the roots are complex, which basically means that s is going to be something of the form of 1/2 plus or minus I times gamma minus 1/4. And so, the real solution for this is going to be some square root of r times the cosine of, God, I don't have enough room. hold on. You get this. You get this. That's what S is. Okay. And this is going to be chi is equal or is proportional to some square root of r cosine of the square root of gamma minus 1/4. Times the natural log of r plus delta. So just some phase shift again. And this function will have infinitely many nodes as r goes to 0. Exists infinitely many nodes. And, what that basically means is an infinite number of nodes implies that an infinitely large negative energy, right? Because we're for more and more and more nodes, more and more energies. So the particle will have fallen to the center. Because typically there's only supposed to be like a discrete number of nodes that are available, but if there's infinitely many nodes, then the particle is gone. It's fallen to the center. Okay, and it's fallen really to the center of the potential. And it occurs if the attractive potential is too strong. Okay, and so we can really derive a critical condition, right? The critical condition was 1/4, where we get the multiplicity of that solution for S, right? So we'd say so this is the criticality. So we can derive kind of this basic idea at this point. So for an S wave, okay, let's call it L equals 0, or I guess kind of like so this would correspond to its potential, or a critical potential that looks something like this, exactly. And then basically what we can derive is that any potential more attractive than this near the origin leads to pathology. And the pathology just means that there's an infinite number of nodes, which is not ideal. So that's an interesting kind of case to look at, falling into a potential, or a particle falling into potential. We can really, look at this from a quantum mechanical point of view, now that we have the tools of the Schrödinger equation and, angular momentum and all these things, okay? So, all right. Let's look at the hydrogen atom, okay? So and we have the tools to do this now. So for a potential, let's say U of R is equal to some alpha divided by R, okay? What we can do first is look at the radial equation. Remember, for the Coulomb potential. So let's just do that. Let's see what happens when we add a Coulomb potential in. Of course, it's going to be the same stuff. Nothing new except for this alpha over R minus this L. We're adding in these new kind of terms here. Sorry. What am I doing? L plus 2. There needs to be probably, I think, an H bar as well. H bar squared over 2mr squared. All that equals 0. Okay. So this is like a radial equation for the Coulomb potential. Just adding this guy in here. So we want to look for the discrete spectra. Okay. We're more interested in the bounded states. And the bound state solutions are convenient for us because we'll want to introduce these new variables. So let's call them rho 8m times the magnitude of E, which will be h bar. The reason we're putting the magnitude of E is because it's negative. It just makes it easier. And then n is going to be alpha over h bar times m over 2e. And then, of course, remember that, we're looking in terms of, we're literally looking at essentially symmetric fields, okay? So keep that in mind. The equation then will become, once we substitute this in, you can double check this, but I think it looks something like we're getting rho. We're going to differentiate chi with respect to rho. And, we have this nice, collapse of the equation to look more simple. This looks like rho squared. Okay, chi is equal to 0. And we seek a solution of the form, that has rho in terms of, some of the angular momentums times the rho coordinate again times some w of rho. So look like a w of rho. Okay, looks something like that. We want a solution that looks like this. And what this function here, this function w here must satisfy is something that we call the confluent hypergeometric function or hypergeometric equation. So it's going to look like this. And the reason it's confluent is because it has something to do with specific singularities that we're there's the hypergeometric equation, and then there's like a confluent version of it, which is like a subset of it, paying attention to different singularities. So we'll look at this here. That's for another day in functional analysis, but or more so differential equations. But this w function here, when we do this change of variable, is going to look like this. And the reason this is nice is because we can say for the hypergeometric, for the confluent hypergeometric function, it'll look something like n plus l plus 1. Sorry, it should be minus n plus l plus 1. I think I wrote that. So that would be the first argument of the function. Then we have 2l plus 2, and then the last argument would be rho. Okay? I'm sorry, my rho's and p's are really close together. They look very similar, but for the wave function to be normalizable, so for anything to be normalizable, basically just means for chi to vanish at infinity. This function must not grow like e to the p, okay? So this function here cannot scale in that way. So this only happens if the first argument, basically this only happens if the first argument of the function is a non-positive integer. So if this is if this argument comes out to be non-positive, basically it's not good. Okay, so we need some restriction on this. We need to let this equal negative n. Okay. In sub r. Okay. Where in sub r is equal to 0, 1, 2. Okay, and this is the radial quantum number. Okay, and then n is equal to n sub r plus L plus 1. Then we can have this from our radial quantum number. And of course, n sub r and L are integers, and n must be a positive integer. And this n here is called the principal quantum number. And of course, from our definition of n here, this is the principal quantum number. From the definition of n, we can have that the magnitude of the energy eigenvalues is going to be equal to m times alpha squared, that constant, times 2 h bar squared, n squared, okay, with the principal quantum numbers squared, okay. And since E is less than 0, okay, it's just negative, the discrete energy levels are literally just going to be this for n takes on the values of 1, 2, 3. Okay, so the principal quantum number is gonna start at 1 and just go. Okay. There's a lot on this page, but we're gonna have to erase it. And so for a given n, okay, so given n, the orbital quantum number, okay, so the orbital quantum number L. Sorry, that's a horrible abbreviation. Let me say, given then, L can take on values 0, 1, all the way to n minus 1. Okay, so now we have a new kind of dependence. The energy depends only on n and not on L. Okay, so depends only on n, not on L. Okay, only depends on the principal quantum number. Does not depend on the orbital angular momentum. And what this says is that the energy then, this is the accidental degeneracy. Okay, this is called the accidental degeneracy. Okay, and the accidental degeneracy is specific to the Coulomb potential. So this is very interesting because the total degeneracy level of n, so n's degeneracy level, total degen level n is from n plus 1, I guess n minus 1, sorry, to L is equal to 0. Remember, we have this kind of series for summing over all the angular momentums. It's going to look like 2L plus 1. This actually is n squared. So you can try to prove that for yourself. Just look at your Calc 2 textbook for common sums. But yeah, that's just equal to n squared. So yeah, great. So let's talk about wave functions. All right. So we've done a lot to get the energy eigenlevel or the discrete energy levels for the hydrogen atom. So let's talk about the wave functions for the hydrogen atom. So the normalized radial functions are going to look something like NL of R, and this is going to be some massive normalization constant. It's going to be like 2 over n A naught, and I'll explain what A naught is in a second. Has something, I think it's like, has to do with the Bohr radius, I think, or it's like the Bohr radius. N minus L minus 1 factorial. Yeah, this is a massive term, but I think it's good for you to see. All of this times e to the r. So here's the actual eigenfunction times 2r over in a naught times L. Okay, and then now we have an L function, which is 2L plus 1 times N plus 1. This should be an N, sorry. Times 2R over a naught. Okay, so this is our normalized radial wave function. Okay, cool flex, but okay. And yeah, and also where we need to define this a naught that we just randomly put in. It's h bar squared over ma, and it's called the Bohr radius. Okay, and these L, P, Q, so L with the P and Q argument are called the associated Laguerre polynomials. Okay, so these are the associated Laguerre polynomials. All right, these guys here, and it's pretty interesting. But yeah, that's kind of what the solutions are going to look like for the hydrogen atom. So yeah, that's about it. Let's look at momentum distribution in the hydrogen ground state, though, because that's something that is not exactly trivial. So if we want to determine the probability distribution of the momentum values in the ground state, so that it could take on. So let's say the ground state of the hydrogen atom is where the principal quantum number is 1, L is 0, and M is 0. Okay. Let's say this implies E naught. You can show that, or try to show that from the equations that we used. But using the atomic units, so atomic units basically is just like h bar equals M equals E equals 1, and then this implies that you can derive that A is equal to 1. It just makes the Coulomb, it makes everything easy, okay? Which honestly is optimal when you're doing theoretical physics, to do these types of simplifications or dimensionless kind of, you want to represent things in terms of natural units. They actually have a physical meaning, by the way. It's not just like some mathematical convenience. But, instead of measuring things in terms of some random, like, meter or whatever else our units are based off of, we base things usually just purely on energy, and in terms of distances even, or like energy, which is just like how many proton diameters it takes to do something or whatever, or to measure something, instead of like using rulers or meter sticks. So anyways, it's kind of a rant, but it has physical meaning. So the ground state wave function in the coordinate space, we can basically define it as this. Okay, this is our ground state function. As you can see, 1, 0, 0, right, for our principal quantum number, and then everything else is doing its thing. And then we can have, of course, that they are represented by the radial function that we derived with the Laguerre, as well as the spherical harmonics 0. Okay. This will look something like 1 over the square root of pi times e to the minus r. Okay. So this is the ground state wave function in the coordinate space. Okay. And the wave function in the momentum representation. So let's look at the wave function in the momentum representation. Okay. Is the Fourier transform is equal to the Fourier transform. I don't know if this notation is right, but it's a Fourier transform of this guy. So we're gonna spectrally resolve this guy. We're gonna do a spectral computation. So we have the momentum, or the basically we're trying to get the representation in momentum space. So we can have that. This should be some 2 pi over, I think it's 3/2, right, for Fourier transforms. It looks something like this with the e to the I p dot r or the differential volume. Okay, and we can integrate the integral in spherical coordinates. So we'll choose like the z-axis of the coordinate system along the vector p. So we're going to choose p dot r is equal to pr cosine. I think we did this last time, but it just makes things easier. And let's work out this integral. Okay, let's work out this Fourier transform. So if we have a, we're trying to solve for a in the momentum representation, or the physical quantity f representation. If you remember that from the very first episode, this is really where we're practically using this. Surprised we haven't used it yet, but I think it's essential to use it here. So of course we can break up the integral to go to spherical coordinates, with this Jacobian here. Trying to remember, I think you added r squared as well. And then d minus r e to the, I think it's I p r cosine, okay? Cosine theta, sorry, I just ran out of room. But, this is going to look like 2 pi over 2 pi here. After integrating all of that crap out, just keep the pi. Sorry, I haven't done integrals in so long. I was doing like a integral on like a Discord server. It's like a Feynman type integral where you like convert it into oh, so also you can just say this is d cosine. Very common in physics to do that. It's nice to just integrate with respect to cosine. I mean, it's basically just u sub or change a variable. So yeah, but anyways, I was like doing this interesting Leibniz rule, and then you kind of make a differential equation, and, solve for the like a whole general set of integrals, and then just plug in some parameter, so you can avoid integrating by parts. I don't know, that was fun. I forgot how fun integrals can be sometimes, but also I just feel like they're like not the most I don't know, I just feel like just because you can do integrals doesn't mean you're smart, like, yeah, they're fun, but I feel like there's so many other things that you could do in math besides learning integrals and just grinding them out. I don't know, just like integral b's seems to be like this massive thing. But yeah, we're going to integral from 0 to 1. Okay, so that's going to look like this 1, 0. So let me write all this crap out real quick. So this dr, I think it's gonna get an extra r term. No, it's not. We're just gonna have r squared, er, and then I think we'll have er minus e to the minus ipr, ipr, annual percentage rate. Just kidding. That's not what that means. P from infinity, dr times r sine of pr, e to the r. Okay, so you can probably, I think you can solve this with integral by parts, but also this thing here. I think you have this guy. Let me look at my notes. Hold on. Okay. Made it this far. I think I can just look at the solution now. So it's basically just 1 minus this guy here, you can notice that the imaginary part of this, this is the imaginary part. This here is the imaginary part of this integral. Okay. And so that's interesting. So because this is the imaginary part of that integral, you can just go ahead and exploit that fact and just say that the result is 2p over 1 plus p squared, quantity squared. So the momentum wave function, or in the momentum representation, we have pi p over 2p divided by 1 plus p squared, which then would be 2 pi 1 plus. Okay, yeah, I honestly didn't feel like integrating that. It's integral by parts, but yeah, looks something like this. Okay, so this is this is basically the spectrum that we want. Okay, and so let's make a clear page now that we have that result. So the probability density in the momentum space will be that, right? And so if we try to do the probability of finding the momentum magnitude between, remember, if we want the magnitude of the momentum between here, or let's say on the interval between here and some increment, that probability then, remember from the very first episode, I know it's kind of a while ago, it equals this times p times this guy here. It's going to look like this, and this is equal to, of course that's a solid angle, this would be equal to a, just the volume, general volume element in general, depending on your coordinates, but we're in spherical coordinates, so we can do 4 pi p squared dp. And so the probability distribution then, so this would basically then give us WP dP is equal to pi over 1 plus p squared over squared, 4 pi p squared dP. And I guess if you were to simplify all of this out, we can have, the pi's kind of go away, all of these things. But there's one pi on the bottom. So it'll be, pi times squared 16, sorry. P squared times 1 plus p squared 4 dP. Okay, so this is the probability distribution. Okay, this is what we wanted. So here's the momentum distribution for the hydrogen atom. Or basically the hydrogen atom in the ground state. So it looks like this. Wow. All right, that was a long problem. Here's the last thing we want to cover, because we haven't covered everything yet, but we're almost done. For motion, basically an essentially symmetric field, the last thing we would probably want to cover is motion in a Coulomb field, okay? And let's do this for parabolic coordinates. So the variables in the Schrödinger equation for a Coulomb field can also be separated by this technique using parabolic coordinates. So let's say we have c, eta, and phi defined by x is equal to the square root of psi and eta cosine, okay? And then c eta sine of phi, and then we have some z that will be sorry, not 1 over z, 1 over 2 times z minus eta. This eta, okay? And, I'm not going to go over this, very in depth. Basically, this coordinate system is useful for problems with like a preferred direction. So if like, for example, an atom in an external field, we're to think about atoms in an external field, or this is called the Stark effect. Okay. There's a preferred direction, basically. Preferred direction. Okay. And the wave function would be sought to be in this, you'd want the wave function to be kind of in this form here, where we have some function of z and multiplied with some function of eta times im phi, okay? And the separation would lead to two basically identical ordinary differential equations for in these guys here. So it's not partial, but when we solve these equations for the appropriate boundary conditions again, we should get something like e to the n is equal to 1 over 2n squared with the principal quantum numbers. Okay, and these states would be now labeled by 3 quantum numbers and 2 parabolic quantum numbers. So we'd have the the parabolic quantum numbers. Let's call them n1 and 2. And these would be, of course, non-negative integers. Okay. Sorry I'm going over these really qualitatively, but it's been a really long video. And the magnetic quantum number is the magnetic the magnetic quantum numbers, m. And they are related, actually, in parabolic coordinates. They are related to the principal quantum number as the sum of both of these parabolic quantum numbers plus the magnitude of the magnetic quantum number to be plus 1, because I think it could be negative as well. But anyways, the wave functions in parabolic coordinates would describe states that do not have definite value of L. Okay, so no definite orbital angular momentum L. Okay. There's no definite value of it, except of course in the degenerate case where both of these equal to 0. Okay, both of the parabolic coordinates equal to 0. Instead, they have definite value of the z component of something called the Runge-Lenz vector, or the Runge-Lenz vector, okay? And this is a very interesting vector because it has something to do with Keplerian orbits. Yeah, it's a very strange kind of application, but I guess if you're working within this kind of parabolic coordinate system, that's interesting that you'll come up with this idea of a Runge-Lenz vector as your kind of, I guess, invariant because of your chosen coordinate system. And these wave functions basically are asymmetric with respect to the z equals 0 plane. Of course, trying to measure our orbital angular momentums or in that kind of plane. But this basically is just like this describing a non-uniform charge distribution along the z-axis. And so that's just kind of, I think that's where I'm going to leave this, but parabolic coordinates also, if you are interested in this, you should definitely check that out for spherically or for essentially symmetric fields. But okay, I think we've covered enough for this idea. So hopefully you got something out of this. And in the next episode,